My title of my talk is listed here. So essentially, I'll be talking on um, mid-IR photonics. So first of all, about all-fiber mid-IR light sources. So what is mid-IR? If you take the electromagnetic spectrum, then this is shown as the visible spectrum is here, and you can see the visible spectrum, and then beyond that will be near infrared. So IR radiation beyond the VGR, which is sunlight dispersed by a prism spectrum, will be known as the IR, either near IR, far IR. There are a lot of jargons about classifications of the different portions of the spectrum. Let us not worry too much about it. But what I would like to share with you is that possibly in around 1800, it was someone, an astronomer, William Herschel, who was the first, has given this importance of infrared beyond the VGR spectrum from a prism of a white light. A expanded view of the regime is shown here. So this is, you can see the expanded view in this portion as the infrared is the central region here, wavelength on the upper side in nanometer and frequency on the downside. Now, near infrared or mid-IR infrared, which would be the focus of my talk, it spreads from around 2 to 10 micrometer. It is a notional, again, the boundaries are notional of the overall infrared spectrum. Mid-IR spectrum is, there are some functional regions. So this again, just for the sake of nomenclature, near infrared spreads from 0.75 to 1.4, short wave infrared 1.4 to 3 micron, mid wave infrared as 3 to 8, long wave infrared 8 to 15, and far infrared 15 to 1000 micrometers. It has large number of applications. This wavelength spectrum of mid-IR, it is applied. It finds applications in astronomy, biological imaging, sensing, military like countermeasures against heat-seeking missiles, optical frequency metrology, optical tomography, which is in biophotonics, and molecular fingerprints, like for example in pollution detections and so on. So if you see this particular figure, which shows the transmittance in percentage against wavelength, you can see there are some arrows which are drawn below the figure, and which arrows are identified with certain molecules names. So oxygen, water, CO2, etc., etc. So these wavelengths correspond to a strong absorption by this particular absorption coefficient of these molecules. So some of these are, if you look at the atmosphere, then it's most of these molecules would be present there. And if you shine a light, and you can see these are mostly at the infrared regime, you can see strong absorption at certain wavelengths, and that would be a signature of the presence of the molecule. Also, 5 to 6.5 micrometer is also, again in the infrared, is also considered as a molecular fingerprint regime. It is strong in this band. You get strong absorption for this kind of molecules, hydrocarbons, hydrochlorides, etc., etc. And in particular, 6.1 and 6.45 micrometer constitutes the wavelengths for strong absorption lines of some of the key components of the human tissues, like amides 1, 2, and water molecules. In astronomy, it finds applications like you can see here is a picture of the Andromeda galaxy taken in the visible light in the upper one, and lower one corresponds to the infrared light. You can see the resolution of the picture taken by the infrared light is much, much better and clearer. Similarly, there is again a nebula picture taken by the Hubble Space Telescope of NASA. So visible one is not so clear, whereas if it is, when it is taken in the mid-IR light view, it is much, much clearer. So that way it is attractive for applications in astronomy. Bioimaging and signature is a very recent paper that appeared in Science in October 2020. You can see on the left-hand side, A is a picture of a mouse heart taken in bright field microscopy. Whereas on the right hand side is the mid-IR microscopy, which gives you a much better picture of the object, that is the heart of a mouse in this particular case. Here is a picture of the heat signature of a group of people. This color bar shows on the right hand side shows how colors in the image correspond to temperature. Here is insulating and does not allow heat to escape, so it appears cold. Now, specialty optical fibers, which happen to be one of my research areas of interest. Now, in this context, I would like to share the history of how photonic crystal fibers, came into the picture in modern world. There were a couple of papers in the PRL Physical Review Letter, same issue of 1987, appeared from Bell Lab by Eli Yablanovic and Sajeev John who is from Kerala originally, and he is now settled in the University of Toronto, Canada. They published independently two papers independently in the same issue. And what they suggested was the following: that you consider, for example, you can consider a slab of glass and you make periodic holes in the X direction and in the Y direction, let us say. So these holes will be then occupying only air, or it could be some other material, let's say liquid refractive index. So let us say these are air holes on glass. And if it is a perfectly periodic, it's a two-dimensional periodicity here, they suggested that this lattice of periodic refractive index in a dielectric with the right periodicity, that is spacing, it can generate an optical band gap akin to electronic band gap in semiconductors. Light in this optical band gap will not propagate in the crystal structure except where a defect is created or disrupted the regularity of the periodicity of the lattice. So that is like akin to change in semiconductor properties by dopants. So for example, if I do not create an air hole at the center, then this would be like an absence of one periodic feature. And then, since now it is disrupting the overall periodicity, those frequencies or wavelengths which were blocked by otherwise in the presence of the central hole, they will now be allowed to propagate, and in that medium. So this will mimic like a guided wave propagation in this complex, you can say the structure, a complex structure, what is called as a photonic crystal. These concepts were extended to optical fibers by Philip Russell working around 1982-83, working at ORC, and then he moved to University of Bath and continued this work there and created a very powerful research group there at University of Bath in England. So this is the photonic crystal fibers, the equivalent of this photonic crystal structure that is created by having a stack of glass capillary tubes, and then these are put in within an oven, which provides a very symmetric heating, cylindrical heating, and the whole thing collapses and in a very uniform manner without creating any distortion in the overall structure, and that creates a microstructured optical fiber. Philip Russell himself called this as a photonic crystal fiber. I prefer to call this as a microstructured optical fiber. So a stack of glass is formed as a macroscopic preform. It is fused at about 1800 to 2000 degrees centigrade, and then because these are usually fused silica, requires higher temperature to melt or to soften, and they are drawn into a fiber in a fiber draw tower. So this is the cross section of a photonic crystal or microstructured fiber. You can see that here the high index, this is a bracket, so what I was referring to a glass block. Here the white portions correspond to that block, and those black holes here correspond to those refractive index features like the air holes in the glass block. So at the center, there's an absence of air hole, so this will be solid. So now this is surrounded, this will have some refractive index, and it is surrounded by a periodic pattern of holes. So overall, the surrounding medium will have a refractive index smaller than that of the center. So light can be those band of frequencies which was otherwise were blocked now can propagate through the solid region, thereby mimicking a guided wave propagation in an optical fiber, and it can be explained nicely as a modified total internal reflection phenomena. Fundamental mode is trapped inside the solid high index central region. I can also create a disruption in the periodic structure here. Instead of a solid at the center, I remove part of the solid from the background, so it becomes a bigger hole. It is again a hole, so it is filled up with air, like those black spots or circular spots that you can see in the cross section. Now here, overall refractive index of the surrounding region would be higher than that at the center, and since this is at the center, it is air. So it is something like, there is nothing like a total internal reflecting structure. So therefore, it would be, but it can guide light, and this is guides light by what is known in the literature as photonic band gap effect. Now, it also shows very strong color. As you can see in the picture taken from Scientific American, an article by Abramovich. And this shows the strong wavelength dependent of such a photonic band gap structure. It will be easier to comprehend and answer or understand what is a photonic band gap fiber or photonic band gap effect if I consider a one-dimensional periodicity rather than a two-dimensional periodic structure, and that we call as a Bragg fiber. So one of my former grad students, Sunandi Dasgupta, did her PhD work on this. So this is a Bragg fiber. You have a central low index core of few microns. It's surrounded by periodic cladding of submicron layer thickness of alternately low and high refractive index. So it is very similar to the structure that I have shown, two-dimensional structure I have shown in the previous slide. But now it is symmetric in the phi direction, but along the R direction, radial direction, you can see the alternately bright and high and low refractive index medium in the form of concentric rings around the central region, which is overall refractive index is smaller than that of the surrounding average refractive index. So if I put this one-dimensional structure into its refractive index profile, you can see at the center there is a core which is of reference N0, which is smaller than both N2 and N1 shown on the figure itself, in which the high refractive index claddings is shown as the periodic cladding is shown as N1 refractive index having N1, and the lower portions of the periodic cladding as having N2. So N2 is smaller than N1, but nevertheless both N1 and N2 are higher than N0, and they are periodically spaced, and the period is cap lambda shown here. Each of the high index region is of width D1 and the low index region of width D2. So these are called cladding bilayers. Now, if you study propagation in this, you can show that light will be confined in the core. In general, if you do from the electromagnetic theory, you will say that one will say that in the central region core, we have a smaller refractive index, is surrounded by higher refractive index, eventually again falling into air. So it's a leaky structure. So light, even if you launch into the center, it will immediately leak away into the surrounding media, should leak away in the surrounding media. But if you choose your cladding layers to satisfy what is known as the quarter wave stack condition from theoretical point of view, which implies that this relationship is valid, that means you choose for a given N1, N2, and a given wavelength of propagation, if you choose your D1, D2, which in such a, actually it should be D1 and D2, not L1, L2. It should be, there's a typo here. So if you cannot N1, D1 is equal to K0 N2 D2, if these two are equal to an integral multiple of pi by 2, then the small reflections which will take place at every interface of high and low index, they will add up in phase and giving you a strong confinement of light in the center rather than leaking out of the fiber. So this implies actually a round trip phase through one period, cap lambda, is 2 pi. So if you consider such a structure, this is a guiding structure due to photonic band gap effect. So we have done quite a few. I would not go into details of that. I'll give you a little flavor of our work in this. My colleague Professor Shenoy was also involved as a co-guide in this PhD guidance of Sonali. So these are some of the papers that originated from our PhD work. So now I switch over to optical nonlinearity. You had some very nice introduction to that in the lecture by Professor Thiagarajan earlier. So it so happened that how it originated the term. It was a physicist, Vavilov, who introduced the term nonlinear optics in 1944. Around 1926, along with Levishine, he observed 1.5% reduction in absorption when a uranium-doped glass was exposed to a focused microsecond pulse from the condensed spark. That time laser was not there, and attributed it to the saturation by intense light. So because of the intensity of the light was very high, it got saturated in terms of absorption, and there is no further absorption taking place even though you continue to shine the light. So as a result, he thought that this high intensity light has some effect on the optical properties of the medium. Laser, first made in 1960, you heard from Professor Ghatak's lecture too, being a hot topic in 1961, the following year, Optical Society of America dedicated a session on lasers at its early March 61 spring meeting in Pittsburgh. Intense discussions were taking place during the meeting on how to use it in communication, how to use it in medical engineering like eye surgery, etc., etc. But sitting at one corner, Peter Franken from Michigan State University, he was observing this discussion, but he was thinking of something else. He was calculating mentally that if I consider a 5 kilowatt pulse laser, which is focused to 10 micrometer, it could generate megawatts per centimeters of electric field. We know that electric field in atoms, which bind together a material, is of the order of 10 to the power 8 volts per centimeter. So this back of the kind of envelope calculations he made, assuming a 5 kilowatt laser pulse to be focused in 10 micrometer, he showed that you get an electric field which is about 3 to 4 orders of magnitude below the electric field in an atom. So it is strong enough to significantly affect or ionize the atoms. I quote, he said, I realized that you could do something with it. So Franken recalled it in an interview in 1985 that he gave. That for example, it could be strong enough to realize detectable what is known as the second harmonic frequency or second harmonic wavelength due to nonlinear phenomena in nonlinear dependence of refractive index of a transparent optical material. He hurried back to Michigan without waiting for the end of the conference. He went to Michigan University and he planned to set up some experiments with his colleague Weinrich to validate his idea in quartz crystal, and communicated his results to PRL in July 1961, which got published in the August 15, 1961, in an issue in the PRL issue. July he submitted. Within a month it got published. So what he used was a pump, ruby laser, 695 nanometer, and weak sample harmonic generation he could detect in the form of a rather faint spot at 347 nanometer. This is how modern nonlinear optics was born. Soon after, others at Bell Labs like Georg-Mine, I think their name, through experiments discovered that it was simple harmonic generation at certain angles in a crystal, like KDP, was many times higher than that at others. This is a picture of Georg-Mine with another colleague, Kleinman, and demonstrating what is a KDP crystal. This observation led him to propound the concept of phase matching for maximizing the effect. The phase matching occurs when a pump beam is aligned at an angle for which the refractive index of the birefringent crystal, KDP, at the pump and the second harmonic wavelength are identical. Then we would say that the new frequency which is generated is perfectly phase matched with the input pump beam frequency or wavelength. The crystal birefringence here serve to compensate the chromatic dispersion between the fundamental and the harmonic. So what was the takeaway from this experiment and these observations? Light can alter its frequency as it passes through a nonlinear optical material. In particular, its effect would be strong if you satisfy the so-called phase matching condition. And this is a picture from AT&T archives. So Joe from Bell Lab and Bob Terhume from Ford Motors Research Lab independently published their discoveries on phase matching in the same January 1962 issue of PRL. It's stimulated by the preprint of the Frank and Spieral paper. Nicholas Bloembergen, working then at Harvard University, directed his research group to look what is the theory that underpins this phenomena of second harmonic generation. So his group started working on nonlinear optics. One of his colleagues at that time from the group member, John Steinstrom, mentioned in some context, I quote, Nico was the intellectual spark plug behind that collaboration, July 61 to early 62, between the experimentalists and theorists in Bloembergen's group. Apparently, Bloembergen was on sabbatical leave at that time, but he used to come to the lab every morning for 2 to 3 hours and motivate his group. That study resulted in a 22-page paper submitted in April 62 in Physical Review, and it was published in September 62 issue of Physical Review. You see, the things are happening very quick. 1960 was the Maimann's discovery of making of the ruby laser, followed by in 61 some theoretical ideas about phase matching and so on, and finally and then observation, specifically more observation, which drove to develop a theory behind it, and that led to this particular publication in Physical Review in September 62 issue. So this, if I plot as a basic physics, if I plot polarization, dielectric polarization as a function of the electric field, of the electromagnetic wave, then that it is proportional to the electric field as long as we are in the linear media. So polarization is proportional to epsilon electric field, and the proportional constants are represented in terms of epsilon naught and susceptibility of first order, electrical susceptibility of first order. But in a nonlinear medium, the P cannot be written in one term. It would be something like a Taylor series expansion. So polarization can be described by having a Taylor series expansion in terms of several terms of nonlinear terms. So chi1 is the very weak. Chi1 is one electrical susceptibility in the linear region. Chi2 is a nonlinear susceptibility coefficient. Then Chi3 is another nonlinear susceptibility coefficient, and so on. Subsequent terms are, of course, by virtue of the Taylor series expansion, would be smaller than the previous term. Now, in glass, the Chi2 term is very weak, so it cannot give you any nonlinearity easily. Whereas Chi3 term leads to a refractive index variation. You can show it by substituting in the above equation that it is essentially represents a refractive index which is dependent on the intensity of the light, of the propagating light. N2 is a nonlinear contribution to the refractive index of silica, and that is very small number, 3.2 10 to the power minus 20 meter square per watt. However, if you consider the propagation of this high intensity light through an optical fiber, which would be of the order of few kilometers, the effect could be substantial. So it is an intensity dependent refractive index which arose out of this theory. That Physical Review paper contained a wealth of knowledge, as told to me by Bob Boyd from University of Rochester once. You know that he has written a very nice book on nonlinear optics. And he said, whenever we thought of something new we have discovered, we found that, it is somehow hinted in that particular paper. In this particular paper, the Bloembergen's group also generalized the problem beyond harmonic generation through four-wave interactions, which is called the four-wave mixing. So mathematical foundation of nonlinear optics reported in this went a long way paper or impact the growth of this new field of research. Other researchers from other groups like from Russia, Reed and Russia enriched other contributing factors to nonlinear optics like stimulated Raman scattering, stimulated Bilon scattering, self-focusing Akhmanov, discovered by Akhmanov, and so on. And solitons, on the other hand, solitons in Japan, discovered by Hasegawa's group in mid-1970. One of the very interesting nonlinear optical phenomena has been what is known as the supercontinuum light. Seed for supercontinuum light was actually planted by Alfano and Shapiro in a paper in 1970, in a PRL paper in 1970, March issue, and where they showed spectral broadening in crystal and glasses if these are pumped by a picosecond pulses from a frequency double neodymium EAG laser. Neodymium EAG laser's frequency doubling would be around the green region. Higher the pump power, broader the bandwidth of the broadened spectrum. Now, in the photonic crystal fiber, you can create a very strong nonlinear optical medium by having a choice of your structure in such a. For example, here is a highly nonlinear fiber shown at the left. It shows that you have a central solid region surrounded by big sized holes. So overall, you have an average refractive index of the surrounding region, which constitutes these holes, is pretty small because the glass is very little fraction of it, and the center you have glass, so you get a very high refractive index, high numerical aperture fiber, and as a result, you can, as a high numerical aperture, you can confine light to a the small solid area in a very strongly. So as a result, you get very easily just nonlinear optical effect in such a structure. So ultra short supercontinuum light is generated when an ultra short high peak power pulse of light undergoes an extreme broadening in a suitable nonlinear medium due to nonlinear effects. So you send in an optical pulse of high power so that you get strong nonlinear effect, and it goes through that medium which exhibits strong nonlinearity. You get at the output a very broad spectrum. So as if you have from a single wavelength, almost single wavelength, you have got a vivid spectrum out of it. In the bottom of that spectrum, you can see the prism dispersed supercontinuum light. This light is called supercontinuum. Theoretically, it can be explained as a combination of several nonlinear effects: Fourier mixing, self-phase modulation, cross-phase modulation, stimulated Raman scattering, and so on. This is a picture on a piece of paper of a supercontinuum light. It was first reported in the case of an optical fiber and a microstructured fiber as a very suitable medium to observe supercontinuum in a conference, ECOC, European Conference on Optical Communication in 1998 in Europe, and eventually published in journal. And this is, you can see the authors showing the picture in which they were carrying out this supercontinuum generation. So they had an 800 nanometer pulse, which is acted as a pump, and they shown it into a photonic crystal fiber, only a few centimeters long, and that gave, on the other side, you get a broad spectrum, as you can see here, power versus wavelength. This also appears in the cover page of my picture. This was photograph courtesy Professor Wayne Knox, who was the director of Institute of Optics Rochester at the time. So he shows a tapered microstructured optical fiber, only a few centimeters. Its input is a femtosecond pulse from a Stye-Sapphire laser at 980 nanometer, and you get on the output supercontinuum light. We studied this, or theoretically we had investigated supercontinuum or spectral broadening in a solid core Bragg fiber that was published in JLT. We continued for a little while in that direction. We then proposed that we can get supercontinuum light in a Bragg fiber. We designed a suitable Bragg fiber and showed that indeed it is feasible, but this is a one-dimensional microstructure fiber, and we eventually demonstrated experimentally that indeed what we predicted is true in this particular optics Rochester paper. And so this fiber was designed by us. It was fabricated by my friend Sisolyatin and his colleagues at Russian Academy of Science. You can see the structure here, Bragg fiber, and this is the refractive index profile. And eventually it was measured in my school friend Ajay Kaur's lab, and one of my grad students went over there, Nagaraju, and they had carried out this experiment, and they showed that in that particular fiber, which was made by the Russian collaborators based on our design, indeed showed in a 3 centimeter length of supercontinuum light. It was powered by a parametric oscillator, and this at around 1100, just little, about 1000 nanometer, and you get a broad spectrum of light as different power level of the input light. Supercontinuum light is extremely useful in optical coherence tomography, which is essentially a Michelson interferometer. Now, I go over to few of our fiber designs for mid-air based on nonlinear effect. So, need for mid-air fiber optic source. We propose that we can make an all-fiber mid-air source by exploiting nonlinear effect. So, what is otherwise available today is what are known as the quantum cascade lasers. A fantastic group on this is Professor Capasso at Harvard University, but he discovered the quantum cascade lasers while he was working in the Bell Lab. Examples of quantum cascade lasers are based on, they're all mostly semiconductor materials, and the different wavelength region, they can give you light in the mid-infrared. But one of the problems which have been disadvantage to some extent for its easy use was that many of it required cryogenic temperature, so it requires cryogenic cooling. Although in very recent talk, Professor Capasso had said that they have now come out with a quantum cascade lasers configuration where they can operate almost at room temperature. So we thought I had a project from Naval Research Labs funded by the US Navy, alternate route to exploit nonlinear optical effect to generate light at the mid-air wavelength. So we exploited nonlinear effects like four-way mixing in a well-designed application-specific specialty fibers and availability of kilowatt level single mode lasers. So this is the material transmitters. What kind of material should be useful for use in the mid-infrared region? And we found out that in particular the chalcogenide materials like of this kind, AS2, S3 and AS2, SE3, whose refractive index and N2 values are shown here, and transmission windows in the mid-infrared is shown here. These were used as a base material for designing our microstructure optical fibers for supercontinuum generation. So four-way mixing, this was explained by Professor Tyagarajan to an extent. So essentially you mix two pump wavelengths. In terms of photon picture, you can say the two pump photons will generate another photon at a longer wavelength and another photon at a shorter wavelength. This is called a non-degenerate four-way mixing. And if the pump is the same and there is not two pumps, it's sufficiently strong pump, that means two photons from the pump will give you a signal and an idler, which is called a degenerate four-way mixing process. So the wave frequency is smaller, means signal will have a longer wavelength, and then the pump and idler is larger, greater frequency, which means a greater wave, idler wavelength would be, sorry, greater frequency. So idler wavelength would be shorter than the pump wavelength. Its origin comes from the third order susceptibility in the expansion of the polarization. So for degenerate four-way mixing, you have WP and W2P is the same for the degenerate mixing, and for variation of amplitude of, to study that, we won't go into the details, but these are described in Govinda Agarwal's book on nonlinear fiber optics. So we study the propagation or evolution of the pump amplitude with propagation, followed by evolution of the idler with propagation, and in evolution of the signal with propagation. Then they are given in terms of this kind of an equation. First term corresponds to loss, the second two terms corresponds to self-phase modulation and cross-phase modulation, and the third terms correspond to four-way mixing. So this this coupled wave, this different coupled equations are then studied to eventually get the results from our designs. It requires four-way mixing for a phase matching process, which is described in terms of frequency as this, and in terms of momentum vector delta K as this must be 0. As a result, a strong pump at WP will create two sidebands at omega S and omega I with a frequency shift from the pump given by this, and pictorially you can represent it in this particular form. It turns out that four-way mixing process becomes stronger and more efficient if you mix a part of the idler output, you feed it back into the input along with the pump in the nonlinear medium, which in our case is a chalcogenide microstructured fiber. And so the photo mixing requires conservations of energy and momentum in terms of these equations. So we found out that our idea was to make use of a commercially available lasers as a pump and create and exploit photo mixing in a suitably designed microstructure nonlinear fiber to generate signal and idler. So you can see here for the 3 dot pump laser of 2.5 at 2.04 micrometer, we can see from this diagram that we get a much stronger signal, much and very weaker idler. So most of the energy pump is used up in getting the signal. So this is one of the critical design feature of such medium to act as an all-time mid-IR light source. So this is one of our first papers. So design features essentially is a microstructure core, microstructure fiber with a central region of higher refractive index, then the surrounding cladding region, microstructure cladding of air and this medium glass of chalcogenide glass. And we chose, after a lot of study, we chose the second ring as of a slightly different, larger radius as compared to the other refractive index features in such a structure, and showed that we can generate good radiation in the IR around 4 micrometer. So pump was 2.05 micrometer at a pump power of 5 watt when other nonlinear effects are not, threshold is not crossed. Photo mixing is the most dominant nonlinear effect. We can see that. I should go to the next slide. And okay, this is more detailed, so let us not worry about it. Now, finally, another design feature was that we designed the fiber in such a way that its zero dispersion wavelength matches closely the pump wavelength. Then the nonlinear effect is stronger. Briefly, it was discussed by Professor Tyagarajan in his talk also. I can refer to that. And so that you get an amplified output of the signal, which is shown in the right-hand side figure. These are the parameters for which we got this spectrum. And we had an efficiency about 17.6%. And full wave half maximum width was 16 nanometer. So this is 16 nanometer with light, which is generated around 4.3, 4.4 micrometer of the mid-IR spectrum. We similar ideas on different structures we did. One around 6 micrometer we did, so we'll not go into those details. 6.45 micrometer, as I mentioned, is important for biomedical applications. Tissues in the human body apparently contains about 35% protein, and so at strong absorption is at around 6 micrometers. So we designed another fiber which would give you light with assuming pump at the carbon monoxide laser, which is commercially available at 5.59, so that the designed fiber zero dispersion is at 5.676 micrometer, close to the pump, and we get a strong nonlinear photo mixing process, and we get a generated output centered around 6.46 micrometer of a bandwidth of 35 nanometers. Average power transfer efficiency was 33%. We went ahead and designing more such fibers for broadband source, and these are the papers. So maybe I'll just keep those. These are all there in those publications. For example, this is bandwidth is about 1.25 micrometer. Structure was borosilicate glass and H2S3 chalcogenide, and pump was a zirconia dope, erbium dope zirconia fiber laser at 2.27 micrometer. We also got another 5 to 6.3 micrometer broadband source, as it is shown here, with a full wave half maxima of about 6.3 micrometer, and the efficiency was about power conversion efficiency of 40%. So these are some of our work on nonlinear, exciting nonlinear effects in microstructure chalcogenide fibers to realize all fiber source, light source at the mid-infrared region. It has been mid-IR, so is because of the strong absorption band in the mid-IR of certain gases, circularly noxious gases like NO2, NH3. You can also design sensors based on nonlinear material to create optical sensors for mid-infrared to sense those noxious gases in the mid-infrared, whose absorption lies there. Now, besides that, I would like to share this slide with you to tell that there is a necessity to reduce humongous power consumption that in internet traffic or cloud servers consume today. Now, estimated annual global data traffic is about zettabyte. 1 zettabyte is 1 billion terabyte. According to a Cisco Global report, by 2020, we will have internet traffic growth at the rate of almost tracking signals or data at the rate of about 5.3 zettabyte across the world. Primarily driven by applications like IoT and social networking, streaming media, video, etc. But this increased data transfer comes at a cost. A single internet search consumes about 1 kilojoule of energy, according to Google, and 200 terawatt hours energy is being used by data centers annually. Many of these issues could be substantially mitigated if cables and switches were configured to communicate using photons rather than electrons or monolithic integration of both. So CMOS technology is the ideal platform. It's a very mature semiconductor industry technology, complementary metal oxide semiconductor technology, which is compatible for this integration of photons and electrons, or photonic integrated circuits and integrated electronic integrated circuits. If you can do that, you can substantially reduce the power consumption in those cloud servers. Example, typical photonic integrated circuit components shown here: delay lines, ring resonators, Y-wave, split waveguides, grating couplers, and so on. And there's a Mach-Zehnder interferometer and directional coupler at the bottom picture that is shown. The types of waveguides for silicon suitable for photonic integrated circuits could be channel waveguide, ridge waveguide, a photonic crystal waveguide, or a slot waveguide. This is taken from a paper, very famous paper now, appeared in 2005 in Journal of Light Ray Technology by Michelle Lipson, who is now in Columbia. At that time, university, at the time she was in Cornell. The guides, silicon slot waveguide, guides strongly confined light in a sub-wavelength scale. Low index region, when these are low index region, is sandwiched between two high index slabs. So this is two configuration of silicon slot waveguide. Silicon on two sides with a very, very small few nanometer air gap in between them. This is a vertical slot and is a MATLAB computed wave pattern, confinement of light in the slot, and this is a horizontal slot pattern. This is the corresponding plot for H field, horizontal slot in the slot region. So you can see very strong confinement of light in the slot region because there's a evanescent field is very strong there. The slot waveguide was first proposed from Cornell University in this paper, and continuity of the normal component of D at the high index contrast interface requires these two should be equal, the normal component of the low refractive index and the high refractive index region, and these two then you convert it into an electrical field, and then you can show by plugging in the refractive indices of the smaller refractive index and the higher refractive index of the two regions, the silicon higher, slot region smaller. You can show that for NS much smaller than NH, if the contrast is high, the ESN normal component of the slot of the smaller refractive index region in the low index slot is higher than ENH in the high index silicon by factor of NH square by NS square. In terms of numbers, for silicon dioxide, silicon silica interface, it comes to 6. If you consider silicon air, it is 12. So you can have a very strong confined light in the slot region. So that has been taken advantage or exploited. And for this kinds of dimension, this is the plot of a normalized field amplitude, electric field amplitude in a slot waveguide. You can see at the central region where the refractive index is 1.46, but the surrounding region is 3.48. You get a very strong electric field at the slot region. So this idea was exploited by us by seeing there is a lot of interest in global industrial trace gas sensors. As you can see, the numbers about $114 billion by 2025 is the expected market. So we did some work in this direction to design slot waveguides to detect certain noxious gases for medical applications or industrial applications. So this is one of our paper which appeared in Sensors and Actuators Again, for the sake of brevity, I will only give you the salient feature of the work. This shows the yellow regions corresponds to the transparency of this kind of material, which is suitable to be integrated with silicon. And this is picture of different kinds of waveguides on silicon. And this picture, as we have showed earlier, that you can get in the slot region very high confinement of the field. So if you fill it up with the gas or the environment, and if it has a strong absorption at that particular wavelength at which you excite the mode in that structure, then you can sense the presence of that material. So NHC gas sensing we did, we will get something like, is very important because it's permissible exposure to NH3 is of the order of 25 ppm for 8 hours and only 35 ppm for 15 minutes. 50 ppm may produce immediate irritation to the eye, skin, and upper respiratory tract. The human threshold limit is 25 ppm. So we consider the structure of this kind. This is the plot of the confined field in the slot. It's a silicon on both sides, air in between with a gap. And then minimum detectable concentration is given by this kind of an expression. And this is the Beer-Embers law in the red equation. This is the fractional modal power. We analyzed all these things and showed that you can, in fact, detect even 2 parts per million of ammonia at the 3 micron, whose exertion is strong at 3 micron in our designed silicon-based slot waveguide. In another one, we did an N2O gas detection in the mid-eye infrared, that is at 4.47 micrometer absorption. We designed, again, it is also very small. It is a ozone, and it is a greenhouse gas and largely responsible for depletion of stratospheric ozone. Long-term exposure may cause adverse effect on reproductive system, audiovisual ability, and so on. So this is a slot structure shown here. This is a single slot waveguide, and also there's a double slot waveguide and corresponding field, calculated field and confined light in the slot region is shown in these 2 figures. So just to give you as a sample. So minimum concentration and fractional power for which is confined in the central region for different gases is shown here. You can see for N2O gas, our design structure can give you 68% confinement at 4.47 micrometer. Carbon monoxide has a strong absorption at 4.6 micrometer. It can give you 66.6% confinement. And CH4 methane is also 3.67 micrometer absorption. It can confine light up to 60.554%. So therefore, if you keep the sensor in the environment containing any of these gases, you can actually sense them through the loss in transmission of light and this way. Finally, we did some of the components which are required in silicon integrated photonics, because silicon-based integrated optics is a high refractive index, high refractive contrast refractive index medium. So I'm close to 1 hour. So polarization diversity scheme has been proposed to get over the polarity, because if you in a waveguide theory, if you want to find out the Morse, you solve the wave equation. If the refractive index contrast between the core and the surrounding region is small, a scalar wave equation is good enough to simulate the model or model the propagation in such structures and find out the Morse in those. But if the refractive index contrast is large, then you need to apply a vector wave equation, and then it becomes highly polarization sensitive. And to reduce the sensitivity of the polarization or strong sensitivity to polarization, or to accommodate the high polarization sensitivity of such components which are required in photonic integrated circuits, somebody has given the jargon, the polarization diversity schemes. You need several polarization components like combiner, splitter, rotator, and so on. This is from a paper from 2007. So one of our work was on a silicon on calcium fluoride based ultra compact, highly efficient. Last year it was published in optical engineering polarization splitter for the mid infrared. So structure is something like this. You have a slot waveguide on the left and a strip waveguide on the right side. Both are based on the substrate of calcium fluoride, and calcium fluoride is also filling out the slot region of the slot waveguide. And this is on the right hand side is the 3D view of the structure. So you can use this as a directional coupler of a certain gap G between these two waveguides and exploit the coupled mode theory to show that if you inject in the strip waveguide TE and TM mode, then over a coupling length, which you can calculate from the coupled mode theory, the TM mode would get completely transferred to the slot waveguide, and with very little TE and TE mode remains in the throughput port. So effectively, what I have gained by doing this, I've got a directional coupler based polarization splitter of TM and TE mode. So these are different parameters as these are designated on the structure itself. And these are the optimized parameters that we had obtained. And normalized power transmission, when we studied that, you can see that in the bottom figure that if you inject TM import in the strip waveguide, all the TM mode light has gone into the slot waveguide, and TE remained in the strip waveguide. So TM output is shown in the red as the transmission, and whereas as a function of different gaps, you can optimize the structure on that basis. At 4.4 micrometer, throughput port light as output is shown in the form of a blacks. Same thing here for if you inject T as input, it does not cross over to the slot waveguide. It continues to remain in the T waveguide. So you can, by this you have been able to get a polarization splitter. This is another work that we did on polarization rotator. There were two works on polarization rotators that we did, but I don't think I'll have time to discuss that. These are relatively recent paper. Polarization rotator for 4.47 micrometer is a similar structure, a strip waveguide and a slot waveguide, but the parameters are to be suitably chosen to change the polarization state of the propagating light. This is the result shown for a polarization rotator that appeared in that book, in that paper. And this is another one on the double slot waveguide. We had studied the efficiency of polarization rotation, which is better with a double slot waveguide. So with this, I think I am just around 12:34. I started at about 12:35. I just end my talk with a big thank you note for your patience to listen for 1 hour to me.